So good afternoon, everyone, and welcome to the course Sustainable Engineering Concepts and Life Cycle Analysis. So I will be basically be the problem-solving instructor for this NPTEL course this semester. My name is Saurav. I am a PMRF PhD scholar from IIT Ropar. So basically, the mandate that has been assigned to me is to firstly cover the whole course as a revision for you all each week, and then carry on with the problem solving by taking a number of examples, so that you can understand the lectures pertaining to that week in a very solid form, and retain those concepts so that you have a good understanding of this subject. So I will be in the, basically I will be covering the whole I will be revising the whole lecture I will be covering the lectures for the whole week, and I will be basically following the course content of the contents of the course instructor, basically, so that I don't leave behind anything, and also I don't deviate. So basically, after covering that, I will go to the problem solving session, and so therefore I have taken a duration of 2 hours for completely and completing the entire assignment. So let us start with the course. Therefore, so the first lecture, basically, it is the life cycle assessment introduction. So what is if we say, like, basically the environmental and natural resource that have gained prominence in the after the later half of 20th century, it has been a very it has been a very significant trend in today's world. That is because of the growing population, affluence or affordability that have increased the pressure on air, water, arable land, and raw materials. So the concern over the ability of natural resources and environmental systems to support the needs and wants of global populations now and in the future, and as part of the emerging awareness of the concept of sustainability. So basically, the the requirement of sustainability has been a very big issue in today's world because of various concerns and various issues related to pollution and various other global warming and various other factors. So that's why people are trying to find out various green ways and sustainable ways and use practices which can help in the creation of sustainability in various domains. So in this regard, if we say what is sustainability, so as per the Brundtland Commission in 1987, they coined this very famous statement. So sustainability basically is the development that meets the needs of the present without compromising the ability of future generations to meet their own demands or needs. So basically, it is about how we can ensure or we can judicially use the resources so that we can meet our own demands, as well as also we don't compromise the ability of future generations to meet their demands as well. So it is like a management way, it is a management, basically, how we manage the resources so that everyone has their stake on that and no one gets compromised. So it is a very powerful but abstract concept, obviously, because it can be touched. It is not tangible. We can see, touch, or hear it. And in engineering, we incorporate sustainability in products, processes, systems, and in integration of environmental, economic, and social factors in design. And in converting the concepts into quantitative design tools and performance metrics that can be applied in engineering design. It is basically a challenge, basically, the sustainability. Although it looks very powerful, it is very glamorous, as to say, but it is like applying the application part is the problem, main issue. So in this regard, people have tried to study this uh, in last century, as well as it is ongoing. It has become a very big issue today's world. So people had started from last century as onwards. So from that, they have few people have like a few prominent names such as Ehrlich and Holren. In 1971, they had coined this equation, which is called the IPET equation. So this equation was coined in order to grasp the magnitude of the pressure on resource and ecosystem. So this basically equation, it relates impact to population, affluence, and technology. So according to them, in the IPED equation, I is equal to P into A into T, that is impact is equal to population, affluence, and technology. So the world population, it is basically increasing at a rate of 1 to 2% and peaking at around 10 billion in today's world, uh, roughly. So the affluence, it basically comes from the fact that the GDP is growing day by day. So average it is between 2 to 4%, and in maximum it is around 8%. So if this type of trends continue for several decades, then compound growth will lead to economic world economic output, and that will increase by 50% in 10 years and around 300% in 25 years, and by more than a factor of 10 in 50 years. So invoking the IPET equation, if technology remains static, then the energy use, material use, and environmental impact will grow 10 times in 50 years, and therefore we need to reduce the impact of technology by a factor of 10 to support 10 billion people, all aspiring to better living standard. So in USA, the relation between the supply sources and the demand sectors have been shown in this figure. So there are various supply sources such as petroleum, natural gas, coal, renewable, nuclear. So the percentage contribution of each of the sources to the demand sectors, and also the percentage of demand, the percentages for each demand sectors which are contributed from the supply sources. So they have been shown in percentages here, and it has been shown in quadrillion British thermal units, so per year. So this is the values given are in per year terms. So also if you see here, this is the sorry, this is the primary energy production of 2009 as per 2009 data. And if you observe here, like in our country India, so the main primary source of energy production is basically the coal. So it is between 20 to 100, about 95, so it is around 70 80%, so 70 to 80%. Whereas in other countries like Canada and all, so they basically depended mainly on crude oil and natural gas. Same was with Russia and USA. So in case of USA, it was balanced in like it was balanced. Basically, it came from crude oil as well as crude oil, natural gas, coal, nuclear. So everyone had contributed. In China, basically, it came from coal, like India only. Same was the case with Australia, Germany, and in France, the nuclear source was the primary source. So this was the in 2009, these were the primary sources of some of the countries. So similarly, in 2008, the major global energy production and consumption have been shown here. So if we can see here, in case of India, so the production was less as compared to consumption. So there, that meant that we had to take energy. We had to take energy from outside. Basically, we took oil from Saudi Arabia and various other countries. So that's the, and Russia also recently. So like that was the way how the energy requirements were met. But some countries had over capacity, like the case of Russia. So the production was more as compared to consumption. So they had surplus. So energy losses. So these losses, they come in various ways. So one can be the loss in terms of electric due to electric power generation. The second can be fossil fuel burning to heat. So the convert so it basically is converted to mechanical work. So that is a turning a generator with steam made from the heat from burning the fuel. So that also result in losses. And one can be one type of energy loss can be the waste heat. So that is the heat that is released as hot water and hot gases. So, going into this, so we can talk about energy efficiency. So, that is basically the percentage of energy input that does useful work in an energy conversion system. So, if you give 100, say 100 kilowatt hour kWh, kilowatt hour of energy. So, how much energy is actually converted as the form of output? So, maximum will be in the form of loss. Okay, so the amount, the percentage which is converted in terms of output, so that is basically the energy efficiency. So these are some of the efficiencies mentioned for some of the objects. So in the case of fuel cell, the efficiency is 60%, which is a very good value. In the case of steam turbine, it is lesser, 45%. The human body has an energy efficiency of 20 to 25%. The fluorescent light, it is basically having a energy efficiency of 22%. The internal combustion engine or gasoline, it is having very less value of 10%. And the incandescent light, that is the light which is which emits which gets illuminated due to owing to heating, so it has a very less efficiency, which is very less, that is 5%. So these are some of the examples of energy efficiencies for various objects. So uh, here the efficiency of some common devices have also been mentioned. So as we saw here, the incandescent lamp or light has the lowest 4-5%, whereas the dry cell flashlight battery, that has the maximum 90%, followed by gas furnaces, storage batteries, etc. So these are some of the efficiencies. So more is the efficiency, better is the quality of the energy source. So this loss basically, so this loss comes into account due to various types of losses. So say if you give the input, fuel input is 100, so various losses are coming. So one is the power plant loss. Okay, so sorry. So during the operation of or the processing of the energy, so 70% gets lost. So then there is the transmission and distribution loss. So when the electricity is supplied through transmission lines, so about 9% gets lost. Then there is motor loss. So the generators and various other machines which basically provide the electricity at the destination, so they also result in losses about 10%. Then there is drivetrain losses, which is basically losses from the machine components which transfer the sources from the energy from the source to the fuel cell basically. And there is pumping loss about 25%. There is throttle loss, so that is basically the controller which decides how much energy has to be inserted in the engine. So that also results in about 33%. There is pipe losses, so that is also one type of transmission loss, which is about 20%. So ultimately from 100 input, we are getting basically 9.5 units of energy output. So that is our efficiency of only 9.5%. So this is the way how the energy loss is basically calculated. So the efficiency of energy use. So the engineers have continuously improved energy efficiency per unit of economic output in both developed and developing economies. So basically, research has been going on how to increase the efficiency per unit economic output. So this why this is important. So this is important because it can improve the energy efficiency, and that will result in the reduction of costs, and as well as it will conserve the natural resources, and also it can reduce the environmental impacts generated from the creation of the energy. So so let's see the environmental impacts associated with energy consumption. So one is the fossil fuel combustion releases CO2, so which is also termed as global warming. So this is lately becoming a very big issue, as can be seen last like 1.5 months back only. So the temperature had risen. So unprecedented temperatures close to 50 degrees centigrade had been felt in India this summer. So that is one of the main causes is the increase in CO2 concentration in the atmosphere. Second is the combustion that also releases oxides of nitrogen, and for some fuels sulfur into air. So these are very harmful gases, and when it converts with oxygen, with reacts with oxygen due to photochemical reaction, it becomes ozone. And that when combined with moisture and water, moisture or rain or clouds, so that will result in acid rain. So that is very dangerous, and that is not good for health basically. And the hydropower generation, it causes land inundation. So the surface get flooded, inundated, and that will result basically in habitat destruction. That's why wherever the hydropower related facilities are built, so nearby people are asked to evacuate, so that there is no issue of loss or casualty due to inundation. So that is basically resulting in habitat destruction and alternation in groundwater and surface water flow. So these are some of the ill consequences of energy consumption. Apart from that, there is this. if we go for nuclear power, there is uranium mining, and that is used for so that is also resulting in it is also damaging the earth, mother earth. And also the issue of nuclear fuel disposal, so that is also a issue. So how to dispose it safely. And if we are going for renewable fuel, that is basically wood, so that is a traditional fuel, so that is resulting in widespread deforestation. So that is also the case why the CO2 is not being able to decrease to a satisfactory level. And that is also adding to the issue, which is already very serious. And apart from that, the solar panel, so although it is a renewable source of energy, but the issue is with the construction of the solar panel. So that is energy intensive, and it uses heavy metals, and that results in creation of metal waste. So although it is a renewable energy, but it also has some side effects. So with this, we come to the end of the first lecture. So now let us start with the second lecture. So the foundation that underlies the world economy, prosperity, and a healthy environment rests largely on how people extract and use the full range of materials that come from and return to the earth, such as wood, minerals, fuels, chemicals, agricultural plants and animals, soil, and rock. The world at large use vast amounts of materials, and those amounts are rapidly basically increasing. So if we can see here, this is a comparison of the material use of USA and the whole world basically in billions of tons. So so the values shown are per capita materials use. So if we focus the curve in trend basically, so we will see that in USA from 1970 to 1995, the increase in the material consumption is very minute. Okay, so from it is about from slightly higher than 2% to up till 3%. It is very minute. But in case of the rest of the world, so if we see here, it is increasing at a very significant rate from about 6 billion tons per capita per person. It is increased up to above 10%. So it is increased by around 60 per 40 30, yeah, around 60%. So it is very serious as compared to, if you see US, it is very negligible as compared to the whole world. So similar is the case with similarly, if we see the material use in USA over the 20th century, as per the United States Geological Survey data of 2002, we will see that the construction materials, so use of construction materials has increased exponentially. Although there were some declining areas that were basically because of some happenings, some situations that had happened, and some incidents that had happened that year, such as recession, oil crisis, World War depression. So leaving that, the increase in construction materials was the trend in increase was very high as compared to others, such as industrial minerals, metals, non-renewable organics, and agricultural and forestry products. So that meant that the construction sector has played a very high role in the in the material use of materials in USA as well as the rest of the world also. So the material use in previous two figures, here one fact to notice here is that the material use in previous figure did not include fuel, and it does not include material that does not enter the economy, such as mining overburden. So the material is only that material which we can see as a finished product, not the one which is used for doing something for which is used as a tertiary way for finding some other thing like for mining. So these are called indirect material flow, and total it is estimated that material use in industrialized country is around 100 pounds per person per day. And materials are, as we all know, limited natural resources, so that is also a issue therefore. So in the past 50 years, it has been found that humans have consumed more resources than in all previous history. The US consumed 57% more materials in the year 2000 than in 1975. The global increase was even higher. In 1900, 41% of materials used were renewable, such as agriculture, fishery, forestry products. By 95%, only 6%. So we can see here that from 41% renewable material use in 1900, we like that declined to very there was a steep decline to about 6% in 1995. So that is a very that is also one of the very serious issue. And the majority of materials now consumed in the developed and developing countries are non-renewable, such as metals, minerals, and fossil fuel derived products. And our reliance on minerals as fundamental ingredients in the manufactured products used, like cell phones, flat screen monitors, paint, to sorry, paint, toothpaste. So that requires the extraction of more than 25,000 pounds of new non-fuel minerals per capita each year. So this rapid rise in material use has led to serious environmental effects such as habitat destruction, biodiversity loss, overly stressed fisheries, and desertification. So the projections are that the projections are basically that between 2000 and 2050, the world population will grow by 50%. The global economic activity will grow by 500%, and global energy and materials use that will grow by 300%. So commenting on the effects of material resource use on the environment, the heads of major research institutes in the in some of the developed countries such as United States, Germany, Japan, Austria, Netherlands, they have noted that unless economic growth can be dramatically decoupled or separated from resource use and waste generation, environmental pressures will increase rapidly. So there is an urgent need to separate the resource use and waste generation, uh, so that the environmental pressure is not increased. So it can be subdued to a certain extent. And so that's a very significant uh, thought basically, is to separate the economic growth from resource use and waste generation. So in this regard, so if we look at flow of materials, so this is basically there are various types of materials used in various segments, such as the process life cycle. If we talk about, so it starts from resource extraction, then it results into material processing, then the product gets designed and manufactured, so then it is sold to consumer and they use it, so it is product use. And thereafter, when the product gets expired, so they basically collect and process those and go for disposal. So this is called renew, recycle, remanufacture, reuse. So these are some of the ways in how we can target each of the chains, each of the blocks in this whole life of the material or the life cycle, and try to improve upon those. So after disposal, this composting is one of the way. So the trends in global material consumption and environmental impact. So the rate of deforestation in the tropics, it is approximately 1 acre per second, and half the world's tropical and temperate forests are now gone. So 75% of marine fisheries are also now overfished or fished to capacity. The freshwater withdrawals have doubled between 60s and 2000s, 1960 and 2000, and various big rivers such as Colorado, Yellow, Ganges, and or Ganga and Nile, they do not reach the ocean in dry seasons. So these are some of the trends. These are some of the trends coming from the or like high material consumption globally, and which is resulting in a serious environmental impact. And that has also resulted in habitat destruction, which has contributed to species disappearance at rates about 1,000 times faster than normal. And over half the agricultural land in dry regions suffer from some degree of deterioration and desertification because of this. So, as available ore grades from some minerals decrease, the amounts of materials that have to be mined and processed to produce equivalent product increases, along with the environmental impacts. And the persistent bioaccumulative and toxic chemicals can now be found throughout the food chain. And between 1970 and 2004, worldwide greenhouse gas emissions increased by 70%. So most of the observed increase in global average temperatures since the mid 20th century is likely due to the increase in greenhouse gas concentrations associated with anthropogenic or human activities sources, including the extraction, processing, use, and disposal of materials. So these are some of the trends that have been found which related global material consumption and environmental impact. So in this regard, The material management approaches can be various. Okay, so these are some of the introduction. Like this first week lecture or the course contents is basically introduction to the whole course. Okay, so these are some of the approaches to reduce the environmental impacts in individual stages. So for the stages A to C, basically these three stages. So we can go for material substitution, replacing toxic or hazardous materials with benign ones, which is called detoxification. Or we can go for cleaner technologies, reduce the toxic or hazardous properties of waste streams. Or we can go for redesign industrial processes to reduce toxic pollution waste. For the keys A to F, that is all for all of them. So we can reduce the greenhouse gas emission associated with fossil fuel combustion and disposal. For the four A to D, so we can go for material regulation, restricting the use of specified materials. For the blocks D to E basically, sorry, we can go for recovery and beneficial recycling of post-industrial and post-consumer waste. That is also called product stewardship. And for the last, that is disposal. Three ways can be used for material management. So one can be waste modification through chemical or biological treatment. One can be waste contaminant or isolation to prevent human and ecological exposure. And one is in situ or on site waste treatment. So these are some of the ways on how we can manage the material as well as improve the life cycle of the product or and make it sustainable. So in this regard, so their question comes, that is, what is the difference between material management as and waste management? So what is the difference basically? So let us see that. So the materials management seeks the most productive use of resources, while waste management seeks to minimize or manage waste or pollutants. Material management basically focuses broadly on impacts and policies relating to all the life cycle stages of a material or product, and that also includes upstream considerations as using less material, using less environmentally intensive material, or making products more durable, as well as downstream solutions such as reuse and recycling. On the other hand, waste management usually focuses only on what to do with waste once they are generated. So, thirdly, materials management is concerned with inputs and outputs from or to the environment, including use of materials, energy, and water, plus multiple environmental impacts, and it is not geographically constrained. However, waste management is concerned mainly with outputs to the environment, such as air, water, and land, and usually only those from waste and only where the waste is managed. Fourthly, the goal of materials management is overall long-term system sustainability, while the goal of waste management is often focused on managing a single set of environmental impacts. Fifthly, the materials management counts as responsible parties all those who are involved in the life cycle of a material or product, including industry and consumers. On the other hand, the waste management usually counts as responsible parties only those who generate waste. So waste is more niche domain or more specific domain, whereas material, it can include everything. Okay. So in this regard, materials management and related concepts. So material management is a very broad concept, and it overlaps and supplements many other concepts being adopted by government, business, and others, including but not limited to this uh, these concepts basically. So one is sustainable materials management. That is a term coined by OECD, or Organization of Economic Cooperation and Development. One is sustainable production and consumption, that is coined by United Nations Economic Environmental Planning, basically UNEP. One is sustainable resource management, also coined by UNEP. One is 3R, that is reduce, reuse, recycle. So this is basically from the G8 nations. One is sound materials society, which is coined by Japan. One is design for the environment, which is coined by Environmental Protection Agency (EPA) and others. Apart from that, there are various terms such as these are very new terms basically, very trending terms. One is green chemistry, one is lean manufacturing, one is sustainable supply chain management, one is eco labeling, one is green procurement, one is zero waste. So, the life cycle materials management approach for environmental for packaging basically as per EPA. So they recommend this diagram. So first is the resource extraction, then goes to material processing, then we go to product design and manufacture, then we go to distribution and retail, then we go for purchase and use, and at last it is end of life recovery. So we will go into deep in the coming weeks and try to understand properly more into more in more depth basically. So now let us go to water. So water, basically the clean fresh water which is suitable for agriculture, industrial uses, or satisfying thirst is becoming increasingly scarce. So in developed world, present total use is approximately 1,000 gallons per person per day. So 1 gallon is basically approx 3.78 liters. So around 4 liter. So it is around 3,780 liters per person per day. That is the total use per person in developed world. So that is very high, and that is for developed basically for developed world, but the general use is the average value is very less. And the sources are surface water, groundwater. So while surface water is renewed on relatively short time scales, groundwater in some cases is a resource that has accumulated over very long periods of time, and it may or may not be replaced at the same rate at which it is withdrawn. So the largest uses basically of water are in agriculture, thermoelectric power, that is power sorry, power generation using a steam cycle, and public supplies. The water withdrawals involve removing water from a surface or groundwater reservoir. If that water is not returned to the same reservoir, the water is referred to as having been consumed. And so the water is lost as steam. For example, the water is lost as steam to atmosphere for power generation, and that results in water consumption. So now let us go to the third lecture, which is LCA and sustainability. So in this regard, so as we just discussed, what was sustainability? So that is basically utilizing your resources carefully without compromising the needs of the future generations. So that is basically the very good, very famous definition given by the Brundtland Commission. So what does it mean for the engineers? So if we check that, we'll find that what is sustainability, basically it is meeting society's present needs without compromising the ability of future generations to meet their own needs. So that is the term coined by, that is the definition coined by Brundtland Commission in 1987. So in this regard, humans are integral part of the natural world, and nature must be preserved. So for this, we have to find solutions such as the triple bottom line solution. So that is basically a solution which is good for the environment, good for economics, as well as good for society. So that is the this synergistic approach. So it has to be there should be relation between environmental protection and resource conservation with economic prosperity and continuity, as well as social well-being and equity. So all these three has to be interrelated. So basically, if we try to go deep, we will understand that basically there are three pillars. One is people, one is planet, and the third one is profit. Sorry. So people, basically it refers that fair practices for all people and does not exploit interest of separate parties based on money, status, or growth. So this means there should be a fair practice for everyone, and there should be no discrimination based on some separate parties which have influence due to money, status, or growth. So it should be equitable. Second is planet. So why planet is important? So that management of renewable and non-renewable resources is possible while reducing waste. So that is important. And why is profit important? So that is the financial benefit which is enjoyed by the majority of society. So these are the three pillars on which we have to work. So therefore we can say that although engineers are part of the problem, we can say, we can accept that yeah, engineers are part of the problem, but they are also a integral part of the solution, because because basically the construction on and the formation of the formation of a nation or its growth is basically dependent on the on the engineers of the country and the work they have done. Okay. So the bill the GDP, as well as the progress which a country brings about, it is also is the main one of the main part played in that regard is the engineer community basically. So we are basically a very integral part of the solution. So Yeah, so we have to keep designing things in a new way. That is the issue. So we will be the problem if we keep designing the things, all the things in the same old way which have been practiced. So engineers of the future need to think differently. So, if we can say, if we can talk about the differently terms, so what is different? What should be different, basically? So, if you see here that the traditional engineering design criteria, so it had basically three factors. One is function, one is cost, and one is safety. So, that was the traditional idea. But if we go for sustainability engineering design criteria, we have to include two more factors apart from that. So function, cost, and safety will remain, but along with that, we have to go for impact on people, that is society, and also impact on the planet, which is the environment. So all these five basically will result in a sustainable engineering design criteria. So the questions for future generations to ask about their designs will be: will it be made from recycled materials? How much energy will it use? Will it be powered by a battery or solar cell? Will it be able to be recycled at the end of its useful life? Will it have parts that contain toxic metals that must be disposed of? So these are some of the questions which future engineers need to ask about, so that we can realize the sustainable engineering design criteria. So the examples of some of the sustainability indicators or metrics for engineering designs. Uh, so if we see here, so the question is, what criteria can we use to compare to engineering designs to determine which is more sustainable? So here are some of the criteria, some examples. It is not limited to them, but these are some of the important ones. So one is the material use, one is the energy use, one is the water use, solid waste generation or ability to be recycled, emissions generation, toxic releases, land impact, etc. So, the so what is the sustainability, and if we go more deep into the topic, so we'll find that there is a relationship between sustainability and the triple bottom line. Okay? So the three pillars of sustainability basically are economic, social, and environment. So economy basically means profit. The social, it basically means people, and the environmental, it basically means planet. So if we see the intersection between economic profit and social people, it basically gives equity. If we see the intersection between economic profit and environmental planet, it will basically result in eco efficiency. And if we go into the intersection between social people and environmental planet, we will basically be getting livability. However, if we go for all the three and find the intersection between them, so it is basically sustainability. So the sustainability, it lies in between. Okay, so it is an intersection of all the three. So as per Elkington in 1997, so in the business community, sustainability is coined a sorry. Sustainability is coined the triple bottom line. So it is expressing that industry has to expand the traditional economic aspects to include environmental as well as social dimensions to create a more sustainable business. So that's the intersection of all the three: economic, environmental, and social. So therefore, what should be the learning objectives for this course or for life cycle analysis? So or sustainability. So that is basically, firstly, state the concept of a life cycle and its various stages as related to assessment of the products. So that is one of the very important objective. The second objective is basically to illustrate the complexity of the life cycle for even simple products. The third step would be to explain why environmental problems like physical products are complex and require broad thinking and broad boundaries. It include all stages of the life cycle. And fourthly, describe what kinds of outcomes we might expect if we fail to use life cycle thinking. So these are some of the very important objectives of the of sustainability and life cycle. So in this regard, the question then comes: why LCA? Why, like, what is the requirement of, or how the LCA is playing a very important role in sustainability? So in the famous definition of sustainability, in meeting needs of present without compromising our ability to meet future needs. So we are faced with some obstacles. One is the corporate and social pressure. One is governmental and regulatory barriers. One is uncertain objectives, goals, and one is lack of tools to measure our progress. So sometimes our intuition is not a sufficient framework for analysis, and therefore LCA can give a systematic method for comparing products and policies in a quantitative manner. So that is the importance of having a life cycle analysis. Now, if we relink cost and environment, we will see that this is a course on sustainability. It has different definitions, but in general, it refers to economic, social, and environmental issues basically, which are being jointly considered. The cost or economic is only one part. We need to understand the others also. And LCA is the kind of tool which will help us to do this. And the final goal is the life cycle thinking. So the analysis basically gives an idea of the life cycle thinking and how we can improvise and improvise and find an even better solution if possible. So the definition basically uh, is that a life cycle of a product. So it takes into account. It is also called cradle to grave. Cradle is basically the baby bed, and grave is basically where the dead bodies are kept. So it is a basically the life cycle generally takes into account from cradle to grave. So it begins with raw materials production and extends to manufacture, use, transport, and waste management. So the design philosophy, so it has various parameters such as material extraction, material processing, manufacturing, use, waste management. And that also like for that to for in order to achieve life cycle, we have to introduce recycle, remanufacture, reuse, and various other terms basically. Sorry. So if we talk about product life cycle thinking, so the life cycle thinking expands the traditional focus on manufacturing processes to incorporate various aspects associated with the product over its entire life cycle. The producer becomes responsible for the products from cradle to grave, and has, for instance, uh, to develop products with improved uh, performance in all phases of the product life cycle. So if we see here, it is a uh, illustrative sketch diagram, so which is showing the life cycle of a product and closing the loop. So basically it starts from here, which is the extraction of raw materials. So the first step, after extraction, it goes into design and production. Thereafter it goes for packaging and distribution and retailing, and thereafter the consumer buys it and uses and maintains it. And after it after its efficiency gets decreased, or the product has finished, so it is either thrown away or it is reused and recycled. So if it is thrown away, so we can go for the main the basic way to go for that is through incineration and disposal. But if we go for recovery, so we if we directly use that and use it for extraction of raw materials, we go for that is called recovery. If we are using that the product which has finished its which has expired, so if we directly take it and using it in design and production, so we are basically we are going for recycling. And if you are using and maintaining it again, so we are basically going for reusing. So that is how the cycle goes on. So the goal of life cycle thinking, so what is the main goal? So the main goal of life cycle thinking is to reduce the resource use and emissions from or to the environment, as well as to improve the social performance in various stages of a product's life. In this way, companies can achieve cleaner products and processes, a competitive advantage in the marketplace, and an improved platform to meet the needs of a changing business climate. So, in this life cycle thinking and pollution prevention, so there are basically a concept of 6RE philosophy. So, this philosophy comes from the fact that the source reduction in a product life cycle perspective is equivalent to eco design principles, and it has been called as the 6RE philosophy. So, RE is because in all the six words, the RE is common in everywhere. So the six RE is basically rethink, reduce, replace, recycle, reuse, and repair. So rethink is basically the product. Uh, The product is, it is basically related to the product and its functions. So the product may be used more efficiently, thereby reducing use of energy and other natural resources. So reduce, that is about rethinking. Second is the reducing, so that is basically reducing the energy and material consumption throughout the product's life cycle. Third is the replace, that is basically replacing harmful substances with more environmentally friendly alternatives. Fourth is the recycling, so that is basically selecting materials that can be recycled and building a product such that it is assembled easier for recycling. Fifth is reuse, that is design the product so parts can be, so that the parts can be reused. Sixth is the repair, so that is make the product easy to repair so that the product does not need any so that product does not yet need to be replaced, so we can easily repair it so that we don't have to replace. So that is the concept of 6RE. Now let us go to LCA and environmental systems. So basically, in environmental system, there is a term called environmental continuum. So that is a basically to show that every the three components of environment, that is air, water, and land, it is in synergy, and that is basically called the environment life. So ecosystem, so we also we can go for so all those generally create an ecosystem. So everything on earth is connected, so that basically living, non-living things, and they depend on each other as well as affect each other. So air, water, atmospheric conditions, plants, animals, soil, all are interlinked, so that they basically create an ecosystem. Sorry. And so basically they are basically a part of the environment continuum. And also there is the WIF nexus. So WIF basically stands for water, environment, energy, and food. So that is the WIF nexus. So it is a relation basically. So so therefore it is having a very important relation. So water basically it is present everywhere and it is very important part of our human health. So how water and health are related? So it is because 80% of diseases in developing countries are due to the lack of access to clean, potable, or usable water. So the pathogens transmitted through water, they kill 25 million people every year by amoeba-linked diarrhea, cholera, and typhoid. And about 3,900 children die every day, as per the WHO 2004 reports. 90% of the 2.2 million deaths of children are under age 5. And the most effective management intervention is basically providing safe drinking water and proper disposal of human waste. So that's the reason why there is a very good important relation between water and health. And it has been found that the diseases from dirty water and lack of basic sanitation, they kill more people every year than all forms of violence, which also include war. So more than war and violence, the diseases from dirty water and lack of basic sanitation have killed more people basically everywhere every year. And that's why it is very important. Further, it has been found that each year more than 5 million people die from water related diseases. A child dies from a water related disease every 15 seconds. 30% of water related diseases, water related deaths, sorry, are due to diarrhea. 84% of water related deaths are in children aging between 0 to 14 years. 98% of water related deaths occur in the developing world. So this is a very huge concern. So the demand for and use of water, so that has various sectors which use this which uses water basically. So one is irrigation, one is commercial, one is livestock, one is hydroelectric. These are the main sectors. One is mining, one is industrial, one is energy, one is domestic. So these are some of the sectors which has a demand for and use of water. So if we see the water consumption by sector, we find that irrigation has about 81%, consumes about 80%, 81% of water, and others, so 3% goes to livestock, and others contribute about 16%. So if we again bifurcate and classify those others, we will find that 1% goes to commercial, 7% is domestic, 3% is thermoelectric, 1% is mining, 3% is industrial. So this is the bifurcation of the percentages of water consumption for every sector. And if we see the worldwide water withdrawals, we will find that here's a graph. Here's a basically a pictorial representation of the percentages of water withdrawal in terms of agriculture, industry, and domestic urban. So if we see in in the in all apart from North America and Europe, if we see in Asia, Latin America, Africa, Oceania, and Caribbean, the agriculture contributes majority of the water withdrawal. So it is 81% in Asia, 71 in Latin America, 86 in Africa, 73 in Oceania, and 69% in Caribbean. Whereas in US and Europe, the major dominant water withdrawal sources are basically industrial. So in North America, it is 48%. In Europe, it is 53%. So that is because agriculture consumes the largest share of fresh water, and uh, in the so overall, if we combine, so it is basically agriculture which is sharing the largest share of fresh water, and that is because Africa, Asia, and Latin America are agricultural economy, and irrigation systems are not always efficient. And although there is a spotlight that booming economies such as China, India, Brazil, they can influence the ratio. However, in industry, in continents like North America and Europe, industry is the major consumer. So that is because they have a more efficient irrigation system, so they don't need much water in agriculture, and also they are basically an industrial economy. So they have more manufacturing units basically. So that's why they have a higher industrial demand of water withdrawal. So, if we talk about individual use, it has been found that a person needs 4 to 5 gallons of water per day to survive. So, that is around roughly 16 to 20, 15 to 20 liters. So, the average American individual uses about 100 to 176 gallons of water at home each day. So, that is around 400 to between 400 600 liters. And the average African family uses about 5 gallons of water each day, which is about again for around 20 liter. In Middle Eastern and Northern African, that is MENA countries, so they are in absolute water scarcity situation because they have only less than 500 meter cube per person per day, and Kuwait has the least per capita water availability, which was 27 meter cube in 1970, 9 meter cube in 2001, and it is projected to decrease to 5 meter cube in 2025. However, Kuwait has the highest per capita water consumption, so it has 200. It requires about 200 liters per person per day. It required 200 liters per person per day in 1980s, and currently it requires 500 liters per person per day. So this is bar graph. This is a bar graph basically representing the per water consumption in cubic meters in 2003. So for various important countries as well as world. So if we see here, the per capita water consumption of India is less than that of the average world. So it is less than 300 also, around 290 meter cube. Whereas the Australia has the highest per water consumption, followed by US, China, and Japan. So the water consumption in major cities are also different as compared to the average national or international averages. For example, the world is urbanizing in by 2050 70%. That is because the world is urbanizing 2000 by 2050 70% of the world's population, they will live in urban areas. In developing countries, cities grow by 5 million residents every month. So that means 5 million more gets added to the city every year in a developing country. So that results in an expansion of slums, and infrastructure does not keep up with the pace of expansion. So that results in the lack of access to adequate water and sanitation facilities. So if we talk about some of the big cities in world, major cities, say for example in Mexico City, so over 21 million people in the metropolitan area. So their domestic water use is up to 364 liter per person per day, which is very high. Similar is with the case of Buenos Aires in Argentina. So about over 12 million people reside in that area, and sorry, and the domestic water use is around 378 to 400 liter per person per day. In Shanghai, China, 23 million inhabitants are present, and the domestic water use is about 411 liter per person per day. Whereas if we compare all those cities with New Delhi in India, so it also contains a huge amount, about 20 million inhabitants of people living there. However, the domestic water use is relatively less. It is around 78 liter per person per day. It is less than 25% of all these values. So the water requirement per use, if we see, so it is uh, it is basically the virtual water. Okay, so there are various types of water. One is the virtual water. So this is the water embedded in food products. So this mainly used in say for example in washing, cleaning and everything. So and so that water can be seen basically. So that's why it's called the virtual water. So seen in the sense like it does not belong to it, it is not applied directly. It is an indirect way of it has an indirect way of application. So that is water embedded in food products. 1000 liters for 1 kg of grain, water is used. Similarly, for 1 kg of beef, about 15,500 liters of water is used. Similarly, in meaty American and European diets, about 5,000 liters of water is used per day. In case of vegetarian, African, and Asian diets, about 2,000 liters of water is used. Similarly, in meat consumption in China, 20 kg per year was used in 1985. 50 kg per year was used in 2009. So this meant equivalent of about 390 kilometer cube of water for meat consumption, and that was equal to the total water use in Europe. So these values are very difficult to reduce or change because of the shift in dietary habits is very impossible to reverse. And if we see the fluid foods, basically the average amount of water needed to grow crops in cubic meters per ton. So we will see that India basically it requires a very high amount as compared to US, China, and Brazil. So in all the four cases, if we see here, so rice, paddy, so it can compete with Brazil and in Kuwait also, but in other cases, soybeans and maize, it is having the maximum. So similarly, if we talk about food waste, so that also results in water waste. So if we see here in developing countries, the main water percentage of water waste is in during farming, during transport and processing, as well as the combination of retail, food price, and home and municipal area. However, in USA, the majority loss in waterways is basically in home and municipal, because other processes don't use much because they have very systematic process of farming, transport, processing, retailing, as well as food service. So that is the basically difference. And similarly, if we see the food losses and waste, per capita food losses and waste in kg per year, so we will see that the food loss and the per capita food loss and waste, so that is, yeah, like in Southeast Asia, the majority is because of the production to retailing stage, and very less is due to consumer. However, in Europe and North America, as well as in Oceania, so the major, like a significant portion of per capita food loss is also due to the consumer. Okay. So yeah, so we come to the end of lecture 4. So let us start the fifth lecture. So that is LCA and water, food and energy. So water use and requirements for energy generation. So water and energy, so it has six basically components. One is security, one is business, environment, justice, policy, sustainable development. So in security comes food, military, energy. In business, it comes opportunities, costs, risks, environment, agriculture, forest, climate, justice, pricing, ownership, equity. And in sustainable development, sanitation, health, poverty, and gender. So, if we relate energy and water, it is found that the energy consumers basically who require water are basically this one, during supply and conveyance, wastewater collection and treatment, distribution, wastewater discharge. So these are some of the consumers who require water. And here are some of the facts basically. So 70%, 75% of municipal water processing and distribution costs is mainly due to the electricity. Okay, so electricity results in about 75% of the municipal electricity uh, covers about 75% of municipal water processing and distribution costs, and the 4% of about 4% of US power needs to be used for this water supply and treatment. So there is a very direct relationship between energy and water. So energy production needs a lot of water similarly. So about 25 gallons is required per kilowatt hour, and 39% of freshwater withdrawals in USA are for thermoelectric plants. Sorry. That is 136 billion gallons per day is required, excluding the hydropower demand. So if we see here, so what is so this slide basically gives information regarding the water use for energy production. So basically, the electricity production is one of the largest users of water. Basically, example of a for a 60-watt incandescent light bulb burning for 12 hours a day for a year in 111 million houses, a power plant would consume about 655 million gallons of water. So that is a very big amount required for lighting an incandescent light bulb. So apart from that, if we check the water use efficiency as per the Virginia Tech study of 2008, it has been found that natural gas takes about 3 gallons per million BTU. Hydroelectric and hydroelectric energy uses around 20 gallons per million BTU. Coal uses 41 to 464 gallons per million BTU. Liquid natural gas takes about 145 gallons per million BTU. Nuclear energy takes about 2400 to 5600 gallons per million BTU. Fossil fuel thermoelectric takes about 230 to 270 gallon per million BTU. Ethanol takes about 2500 to 29,100 gallons per million BTU, and biodiesel around 14,000 to 75,000 gallons per million BTU. So there is an therefore irony that biofuels, although they are green, but it has also some limitations. So it currently uses 2% irrigated water for the energy crops, and if all blends are implemented, about 180 kilometer cube of water will be needed. So that's an irony when it comes to water, although it is a green alternative. So apart from that, if we see, the electricity consumes 20% of water excluding agriculture. So the if we see here, the thermoelectric contributes, it takes about 20% from that. So also there is a concept of hydraulic fracturing. So that is basically inserting some liquid at a high pressure inside the fissures of rocks, so that the cracks can widen, the voids can widen, and from there we can take out some we can take out hidden oils and natural gases. So that is a process largely adopted. So this natural gas is projected to increase by 30% over the next 25 years. Over 1 million wells have already been hydraulically fractured since the 1940s. An estimated 35,000 wells are fractured every year. Hydraulic fracturing uses a mix of water, sand, and chemical additives, and it is used on 90% of wells in the US. So it is a water intensive process. Therefore, 2.3 to 4.8 million gallons per well is required. So 2.3 to 4.8 million gallons of water is required per well. So therefore, it is a very water intensive process. And once used, the water is extremely polluted. So it has to be treated prior to disposal. So it can be directly thrown into the side streams or nearby water sources. So, what are the concerns related to the water related concerns related to fracking? So, the water withdrawals. So, water used in fracking may be competing with other uses, because if it is not properly treated and discharged, so that if we use it for some other purpose, it is polluted. So, it will have significant health related consequences. Apart from that, the groundwater contamination is an issue because of the drilling and production. The proper treatment of wastewater, so it is very important. So also the water, because it will be carried by trucks, so that may result in traffic, creating traffic in a road, or a huge business or a very high traffic area. So that will result in destruction of that area. And also it may impact on water quality. It may result in surface spills from the trucks. And also the stormwater management may be issue, because it can it can mix with the stormwater, and that may pollute the nearby streams and water sources. So what is the global water situation? If we talk about that, we will find that local water shortages are multiplying. Current patterns of use and abuse, the amount being withdrawn dangerously close to the limit and even beyond. An alarming number of rivers no longer reach the sea. The Indus, the Rio Grande, the Colorado, the Murray, Darling, the Yellow River, the arteries of main grain growing areas. So these are some of the alarming situations. Severe and long droughts in Australia, India, Brazil, and South America has been seen. So 2 years ago, hydroelectric power plants did not have enough water to drive turbines, and there were repeated brownouts. That is, electricity was not able to be provided every time. So the global water situation, what is happening? So freshwater fish populations are in precipitous decline. So it is in a steep decline. Sorry. So that is because fish stocks have fallen by 30%, as claimed by WWF for Nature organization, and larger than fall in populations of animals in any ecosystem. So this fall of 30% in fish stocks is larger than any fall in population of animals of a particular any particular ecosystem. And 50% of world's wetlands have been drained, damaged, or destroyed in the 20th century. Fall in volume of freshwater in rivers, invasion of salt water in delta, changing in balance between freshwater and saltwater. Excess pumping of water from rivers feeding Aral Sea in Central Asia led to its collapse in 1980. Global water crisis, impact on supplies of food, generation of energy and other goods. So these are some of the global water situation which are very serious. And if we check about the water consumption in a global view, we will see that so it is basically related to demography. So how is the what is the concentration of people, and what is the topology of the area. So over the past 50 years, the population has increased from 3 billions to 6.5 billions. So if I'm not mistaken, we have recently crossed about 8 or 8.5 billion. So water use has also tripled. So population is like, as per predictions, population is likely to rise by under 2 billion by 2025. So it is around 8.5 billion, and by 3 billion by 2050. So by 2050, it will be around 11.5 billion. So along with that, the demand for water would also rise correspondingly or even more. Not just the absolute number, but the habits and diets that make the biggest difference. If there is no change in agricultural efficiency, the world will need more, as much as 60% more water for agriculture to feed the extra 2 billion mouths. This is roughly 1500 kilometer of water, as much as is used for all purposes in the world outside of Asia. So this is an example of Lake Chad, which got disappeared in Africa. So this was the Chad lake. The water, basically the blue color represents water in 1963. So in 10 years after, like the water reduced by about 50%. So former outline of the lake, it can be seen here in 1973 photo. In 1987, you can see only 10-15% is remaining. And so from that onwards till today, so it is about 5 or 10% to the actual lake, and the rest has been occupied by vegetation. So this has been the situation now. And similarly, there is absolute so this is the representation image representation of absolute scarcity for 1 billion people by 2025. So many countries will import grain, many countries will import greater than 10% of their cereals from other countries because of this issue. So if we see the concentration of physical water scarcity, so it is mostly covering our country India, and a few regions of the African country, as well as the Middle East area. And economic water scarcity, so like most of the regions of Africa, South America, and few places of North America, and also in the China area, so around China, and also in Australia. So these are some of the areas. And little or no water scarcity, so that is mainly yeah, the most of the United States will not have any water scarcity, and also in the Arctic regions basically, and some of the regions have not been estimated. So similarly, if we see the intensifying water scarcity, so declining water tables and focusing on consumption, so the red sorry, so the red color basically represents the extreme stress regions. So the west region and the south region of India, so they basically have an extreme stress of extreme degree of water stress. And the golden brown color basically represents the high stress areas, and then the light brown is the moderate stress, and light yellow and light and deep yellow, they basically light and pale yellow, they basically they denote the low or no stress and minimal water use. So our region basically falls into the water stress area, so that's why it is a very big concern. So we can say that 80% of the water scarcity is attributable to the population rise, so that is self-explanatory. And higher food and energy requirements, so that is leading to higher food and energy requirements, and that is again leading to higher water requirements. And economic development is also one of the reason, so that is basically changing the habits as and diets. In the last 50 years, population from 3 billion to 6.5 billion has increased, so water use has tripled. And projections in 2025 and 2050, so population increased by another 2 billion and 3 billion, so we have reached around 8.5 billion in we will be reaching 8.5 billion in 2025, and by 2050 it will be around 11.5 billion. So greater than 50% people will be water stressed or scarce, so that is a very ominous these are very ominous signs basically. So this is the world population evolution. So as per 2008 data, so the population was around 6.6 billion, and from that only, so they have the United Nation Population Bureau of United Nation has predicted that by so the according to them, the UN, the medium hypothesis is the most likely one. So that is that this is the trend that should follow. For 1995 and 2045 2050, it takes into consideration the decrease of number of children from per woman from 2.82 to 2.15. So in 2008, the number of children per woman was 2.82. So according to the UN, it should decrease to 2.15. As well as there should be improvement of life cycle expectancy from 65 years to 65 years to 76 years. So that is basically the average age a person will live. So it will increase due to medical advancement in medical healthcare and everything. So it will increase from 65 years to 76 years. The natural growth would fall from 1.35% to in 1995 2000 to 0.47 percent in 2045 to 2050. So that is a prediction basically. And the blue line basically represents what would be the demographic evolution if the current birth rate 2. This current birth rate is as per 2008. So if that was maintained, what would be the demographic evolution? So it is showing here, so it is very scary. So if that gets maintained, so as per 2050 it will reach 13 billion, so that is very high. So that is a constant progression. And apart from that, so this is the data of global urban population trend. So it has been found as per world population of 2005 that which had 6.4 billion people. So about 49% were urban and 51% were rural people. And if we talk about the urban population in billions, so we could say this this histograph basically, the bars basically show the low and middle income countries in yellow, and high income countries in light in navy blue. So if we see here, one interesting observation is seen that the number of people, urban population of low and middle income countries is started increasing from 1975 to 2015, whereas in case of high income countries the urban population was constant. So that means there was a high requirement of basic infrastructure and standard of living in low and middle income countries, which force people to move from village to cities and towns. So that is the urban population, whereas because of the presence of adequate facilities, that trend was very limited in the high income countries. So with this, we come to the end of the lecture for the first week. So now let us go for problem solving. So the first question is, which of the following correctly defines the sustainable development concept? A, fulfilling the need of present generation by compromising that of the future generations. B, fulfilling the need of present generation without compromising that of the future generations. C, compromising the need of present generation to ensure the ability to meet that of the future generations. D, compromising the need of present generation by compromising that of the future generations. So which is the correct option? So so for that we can go for the sustainability definition given by Brundtland Commissions. So according to this, sustainability means the development that means that meets the needs of the present without compromising the ability of future generations to meet their own needs. So as per this, the second option, that is fulfilling the need of present generation without compromising that of the future generation, is the correct option. So B is the correct option. As you can see, B, fulfilling the need of present generation without compromising that of the future generations, is the correct option. The second question, which of the following accounts for T in the IPET equation? A, time, B, threshold population, C, technology, D, none of the above. Sorry. So if we see the magnitude of sustainability challenge, so the IPET equation basically it relates impact to population affluence and technology. So I equal to P into A into T. So this T is basically technology. So therefore C, technology, is the correct option. So as you can see, C, technology, it is the correct option. Third question, which one of the following is the least energy efficient system? A, internal combustion engine, B, fuel cell, C, incandescent light, D, human body. Which is the correct option? A, B, C, or D? So if we check the energy efficiency, so the percentage of as we discussed, energy efficiency is the percentage of energy input that does useful work in an energy conversion system. So the fuel cell basically gives 60% energy efficiency, steam turbine 45%, human body 20 to 25%, fluorescent light 22%, internal combustion engine gasoline 10%, incandescent light 5%. So basically internal combustion engine is 10%, fuel cell is 60%, incandescent light is 5%, and human body is 20 to 25%. So if we see, the incandescent light gives the minimum uh, least energy efficient system. So so C, incandescent light, is the correct option. As you can see, C, incandescent light, is the correct option. Fourth question, which of the following statements is or are correct? A, improving energy efficiency helps in reducing cost. B, improving energy efficiency ensures more consumption of natural resources. C, improvement in energy efficiency has nothing to do with environmental impact. D, improving energy efficiency reduces consumption of natural resources. A, B, C, and D. Out of this, which is the correct option, or which are the correct options? So so let us see what is the efficiency of energy use. So engineers have continuously improved energy required per unit of economic output in both developed and developing countries economies. Improving energy efficiency can reduce costs and conserve natural resources. It can also reduce environmental impacts. So therefore, so improving energy efficiency helps in reducing costs, and also improving energy efficiency reduces consumption of natural resources. So these two are the correct statements. That is A and D. Sorry. As you can see, A, improving energy efficiency helps in reducing costs, and D, improving energy efficiency uh, reduces consumption of natural resources, are the correct options. Fifth question, which is the correct order of life cycle material management approach? A, product manufacturing, resource extraction, material processing, distribution, use, end of life recovery. B, material processing, resource extraction, product manufacturing, distribution, use, end of life recovery. C, distribution, resource extraction, material processing, product manufacturing, use, end of life recovery. Or D, resource extraction, material processing, product manufacturing, distribution, use, end of life recovery. A, B, C, D. So which is the correct order of life cycle material management approach? So this is the correct order. If you can see, resource extraction, material processing, product design and manufacture, distribution and retail, purchase and use, end of life recovery. So first is the resource extraction. So if we see here, so D option. Then comes the material processing. So then is the product design and manufacture, this one. Then comes the distribution and retail, this one. Then comes purchase and use, this one. And at last is end of life recovery. So end of life recovery. So D is the correct option. As you can see, B, resource extraction, material processing, product manufacturing, distribution, use, end of life recovery is the correct option. Sixth question, which of the following statements is or are correct? A, groundwater can be renewed quickly. B, surface water needs longer time scale to be replenished compared to groundwater. C, withdrawal involves removing water from groundwater source only. Or D, water withdrawal involves removing water from both surface and groundwater sources. So which is the correct option? A, B, C, or D? So water sources are both surface waters and groundwater. While surface water is renewed on relatively short timescales, groundwater in some cases is a source that has accumulated over very long periods of time and may or may not be replaced at the same rate at which it is withdrawn. Water withdrawals involve removing water from a surface or groundwater reservoir. If that water is not returned to the same reservoir, the water is referred to as having been consumed. Example, water losses into atmosphere from a lake in a power plant. So from this we can say that the correct option is D. Water withdrawal involves removing water from both surface and groundwater sources. So D is the correct option. As you can see, D. Water withdrawal involves removing water from both surface and groundwater sources is the correct option. Seventh question, from which perspective sustainable engineering designs are different from the conventional engineering designs? A. Operational safety. B. Environmental impact. C. Functionality. Or D. Cost effectiveness. A, B, C, D. Out of this, which is the correct options? Sorry. So we see the hint. So the traditional engineering design criteria, so that basically contain functionality, cost, that is cost effectiveness, safety, that is operational safety. And in sustainable engineering design criteria, the above plus impact on people, society, and impact on the planet, that is environment, that is environmental impact. So from which perspective sustainable engineering designs are different from the conventional engineering designs? That is from environmental impact perspective, that is B. So B, environmental impact perspective is the correct option. As you can see, B, environmental impact is the correct option. Next question, what is the 6 RE philosophy in life cycle thinking? A, reduce, remove, replace, recycle, reuse, rethink. B, repair, remove, replace, recycle, reuse, rethink. C, reduce, repair, replace, recycle, reuse, rethink. D, reduce, remove, replace, repair, reuse, rethink. A, B, C, D. Out of this, which is the correct option? So as per the hint, so the six terms, six R, as per the 6 RE philosophy, the 6 R's are rethink. So rethink is in A, B, C, D, all the options. Reduce. So reduce is in C, D, uh, A. So between A, C, and D will be the correct option. So then replace. So replace is in A, C, and D. So between A, C, and D. And then recycle. Recycle is in A, C, and so yeah. So it is not present in D. So it will be between A and C. Then reuse. Reuse is in A as well as C. And repair is in C but not in A. Yeah. So C, reduce, repair, replace, recycle, reuse, rethink. So C will be the correct option. So as you can see, C, reduce, repair, replace, recycle, reuse, rethink is the correct option. So next question, which of the following factors is the highest contributing sector in terms of water consumption? A, irrigation. B, mining industry. C, livestock farming. Or D, electricity. So as per the water consumption per sector, so maximum is in case of irrigation, and others contribute 16%, livestock is 3%. So sorry, so irrigation 81%. So that is the highest contributing sector in terms of water consumption. So A, irrigation is the correct option. So as you can see, A, irrigation is the correct option. So last question, 10th question. Out of the following energy production sources, which two are the least preferable in terms of water use efficiency? A, natural gas. B, liquid natural gas. C, coal. D, biodiesel. So out of A, B, C, and D, which two are the least preferable in terms of water use efficiency? So if you see here, water use for energy production, So we will find it for natural gas, the water use efficiency is 3 gallons per million BTU, British thermal units. For liquid natural gas, it lies between 145 gallons. It is 145 gallons per million BTU. For coal, it is between 41 to 464 gallons per million BTU. And for biodiesel, it is 14,000 to 75,000 gallons per million BTU. So biodiesel is the maximum, followed by coal 41 to 464 gallons per million BTU, followed by liquid natural gas 145 gallons per million BTU, followed by natural gas 3 gallons per million BTU. So the two least preferable in terms of water use efficiency will be biodiesel and coal. So biodiesel and coal will be the correct choice. That is DN, DNC, CND. So CD will be the correct option. Coal and biodiesel. So as you can see, C, coal, and D, biodiesel are the correct options. So with this, we come to the end of today's problem solving session. So we will be meeting next week at the same time and Sunday. So we will start with the second week lecture contents, and we will follow that by the problem solving of some important questions based on that lectures contents. So with this, I would like to end today's presentation as well as today's session. So with this, I am closing this. Thank you.